hopefully you went through and worked the problem that we had indicated on the computer screen. And I say measuring the variability of the random variable. So we know that a random variable varies in a way that we can't determine. But one of the questions that we try to do is to estimate how much variability there is. And so if we look at the problem that you had gone through, the average comes out to be 3. We add these up, it's 30. The mode, the most frequently occurring value, is also 3. And if we come back, we go 1, 2, 3, 4, 5. The middle value, and since there isn't a middle value, we just take the average of these two. And so the median was also equal to 3. When we come over and we do the average of y, that also added up to 30. The average of y was 3. The mode, the most frequently occurring value, was also 3. And if we go 1, 2, 3, 4, 5, the median was also equal to 3. And so if we would go back and simply use the mean, median, and mode, they really don't adequately describe the behavior of the random variable. They were a single number that attempted to describe all the other numbers. Now if we look at this, the mean, median, and mode do a pretty good job of describing it. But the reason is that there is little variability in this particular set of random numbers, whereas in this there is a lot more. Now, one way of looking at the variability would be to draw a distribution. And in this case, the distribution would be drawn this way, where we could go back and say, well, we had 6 of these, 3 values. We had 2 4s and 2 2s. Now, if you look at what the distribution does, it gives us the shape of the variability. And we look at y, we had 3 zeros, we had 1, 1, we had 4 3s, and we had an 8 and a 9. Now, just visually looking at this, it's obvious that x has far less, let me repeat that, far less variability than y has. But this is spatial thinking and thinking in pictures. And it's a wonderful way to think, and we can get a lot of insight into it. But the statistician wanted a number that would describe variability. So this led them on a journey for trying to measure variability. One of the ways, and the easiest way, was to come back and define something called the range, which is the high score minus the low score. If we had taken a census, the range would have been 40 minus 1, or 39. Now, the range suffers kind of from the same malady that the median and the mode suffer from, and that is they waste potential information. We come back and we think of the mode here. The mode was 1, but that in no way described the other numbers. So one of the philosophies in terms of developing ways of describing the random variable was to try and come up with something that used all the numbers. Notice that the mode and the median did not use all the numbers. The mean did. The range doesn't use all the numbers. Now, there is a sample mean or sample range, and the letter R is used for that. And so the range here would have been 4. The range here would have been 7, high minus low. One of the reasons that there is a symbol for this is that in the early years, before the computer and the calculator, people tried to come up with mathematical techniques that were very simple in terms of the arithmetic that was needed. There isn't anything much simpler than subtracting 2 numbers. So you will see the letter R used to indicate this sample range. There isn't a universally accepted symbol for the true range. So we could come back here and say, well, the estimate, the statistic, the range was 4, the other range was 7. Statistics are random variables. Depending on the sample, we'll get different statistics. The 39 here is a parameter. It is the truth, but it is not one that is used extensively. So we move on to other ways of trying to measure variability. If I can get the paper here. We've got the paper straightened out here. And what we're going to look at is a measure of variability where all the numbers are used. And the average, in this case, we're dealing with the census, so we have the true average. We're going to look at how close the individual values were to the true average. The true average, if you remember, was 10. So if I compare 1 to 10, this individual value was 9 units below the average. And I do this for each value. So 1 minus 10 is minus 9. 3 minus 10 is minus 7. 5 minus 10 is a minus 5. 8 minus 10 is a minus 2. And 12 minus 10 is a plus 2. And 40 minus 10 is a positive 30. So the idea was to go back and say, let's add up all of the individual variances or deviations from the mean, see what we get. Well, we have 9, 18, 25, 30, 32, minus 32, and we have a plus 32. And so this adds up to 0. Now this always happens. And this is really a very powerful attribute of the mean. The mean is what is called an unbiased estimator of the data. When we say on an average it's going to cost us $10, let's say, to service a customer, we recognize that sometimes we're going to have overestimated the cost. We said 10 and it was actually 1. We overestimated the cost by $9. Down here we said 10, it was $12. We underestimated the cost by $2. The underestimates, 30 plus 32, will always balance out with the overestimates. These will always add up to 0. Well, their goal was to come up with something that would measure variability. All this indicates is that we've done our arithmetic correctly. So we define another way of measuring variability. And we have the true absolute deviation, or the true MAD, mean absolute deviation. And so what is creating the problems for us is the minus signs. To get rid of the minus signs, we can go back and we can use the absolute value. So if I come back and I look at this particular example, what I can do here is I can go back and I can take the absolute value of these. So all the absolute value does is it says if the number inside is negative, make it a positive. So we go all the way through, and wherever the numbers were negative, we make them positive. Now I add this up, and this will add up to 64. Now this is called the total deviation. And in statistics, it's very important to recognize that the words from the mean are always implied. So this is the total deviation from the mean. It was 64 units from the mean. So if we go through and use our formula here, we can calculate out what would be called the true mean absolute deviation, which was 64, which we had here. We took a census, there were 7 numbers, and this would come out to be 9 1/7. Now notice, though, again, there isn't a Greek symbol here. And what that indicates is that this is not the most important parameter or statistic. If we come back and we do a sample, here the average was 3. 1 minus 3 is minus 2. 3 minus 3 is 0. This is 2. Notice again that this always adds up to 0. We then take the absolute value and the total deviation from the sample mean adds up to 4. So now we can come back and we have the sample average deviation, which is the total deviation, which was 4. We had a sample of 3, so it was 1 1/3. Now, we could go back and do this for the other sample, and in that case, we end up with 8 minus 8 1/3 would give me minus 3 1/3. Minus 8 1/3 gives me a minus 1/3, and minus 8 1/3 gives me a plus 3 2/3. Now notice again that adds up to 0. We take the absolute value, so we have 3 1/3, 1/3, 3 2/3, and we add this, we have 7 1/3. And we could come back and calculate out the average deviation, and we would have 7 1/3 divided by 3. So we would have 22 over 3 divided by 3, which gives me 22 over 9, which is 2 4/9. Now, if we compare our results here, we have the true average deviation was 9 1/7. That was based on a census. And we had the mean absolute deviation on this sample was 1 1/3. And the mean absolute deviation was 2 2/9. These are statistics. They will vary from sample to sample. They are an estimate of the truth. So I'm going to stop here